slide that says resources
Yes.
on Mars?
Yes.
Great.
All right, welcome, Dr. Putzig.
Okay, thank you very much for the introduction. So today I'm going to discuss with you some, let's see if I can put this in present mode. Are you still seeing the slides?
Yes.
Better? Great. Thank you. So I'm going to talk about ice resources on Mars and what we know about them currently, and how we have gathered that knowledge. So quite a bit of what I'll be discussing today comes from the spacecraft depicted in this image, which is the Mars Reconnaissance Orbiter. And one of the key instruments on board for understanding ice, especially in the subsurface, is a shallow radar sounder known as SHARAD. This is actually an Italian designed and operated instrument on board the US Mars Reconnaissance Orbiter spacecraft. Okay, so much of what we know about ice on Mars is really from a set of missions that have been carried out over the last 30 years or so. A primary source of data is the Mars Reconnaissance Orbiter that I mentioned in the previous slide. This was launched in 2005, and it continues to operate and collect large amounts of data at Mars. Major contributions from that spacecraft come from the imagers, the HiRISE and CTX cameras, as well as from surface temperature observations by the Mars Climate Sounder. And of course, I already mentioned the radar sounding data from the shallow radar. So from here on, I'll refer to that shallow radar sounder as SHARAD. This instrument uniquely provides us information about the subsurface from depths of tens to hundreds of meters, and up to about 3 kilometers deep in the polar caps. Earlier instruments on other spacecraft, such as the Mars Odyssey neutron spectrometer and thermal spectrometers, both on Odyssey and on the Mars Global Surveyor, as well as the Mars Global Surveyor's laser altimeter, provide other information that helps us constrain where Martian ice might be. It's important to know that all of the...
I can't see your screen. Okay, there it is. Go ahead. Sorry.
Okay. So one of the important things to understand is that all of these instruments were designed around scientific goals. None of them were explicitly intended to search for resources. And as a result, we're left with few constraints on the properties between depths of about 1 meter and 20 meters. Basically a zone which we can't resolve well with any of the current instrumentation. Unfortunately, this is where one might expect to find the top of the buried ice in the lower latitude or lower mid-latitude regions where current thinking is targeting the human missions, with a goal towards accessing that ice as a resource. So in this presentation, I'll review the Mars Reconnaissance Orbiter shallow radar results, and then I'll discuss a project called the Mars Subsurface Water Ice Mapping, or SWIM project, which has sought to assess mid-latitude ice using data from all of these different instruments aboard these 3 orbiters. Okay, so as I mentioned, SHARAD is provided by the Italian Space Agency, and it flies on board NASA's Mars Reconnaissance Orbiter. So we have a dual lead team. We have our team leader in Italy, who leads up the Italian operations, Pier Francesco Lombardo. And then I serve as the deputy team leader and also the US team leader. And we provide support both for operations and a lot of the scientists that are doing the first analysis of the SHARAD data. We've been in operation coming up on 19 years at Mars. And we've got a vast amount of data, as you'll see. So just to give you an idea of how SHARAD works, I wanted to show this animation that was put together fairly early in the mission, showing the Mars Reconnaissance Orbiter here flying over the surface and its dipole antenna for SHARAD, emitting a signal that bounces off of the surface, and most of that signal comes from directly below the ground track where the yellow line is. And some of that signal penetrates into the subsurface and reveals layering within the subsurface. And in the case of the North Polar Cap here, we get reflections really all the way down through the cleaner part of the ice here, shown in white, into the fuzzier part of the ice, shown in a lighter gray tone, the so-called basal units underneath the cleaner ice. So in general, the objective of this radar instrument is to map what we call dielectric interfaces, which are usually associated with geologic boundaries, and interpret them in terms of what they're telling us about materials in the subsurface, including rock, regolith, water, and ice. Given the orbit altitude of MRO and our transmitted signal, which is a 25 to 15 megahertz signal, so 10 megahertz wide bandwidth signal, we get a range resolution of about 15 meters. So that's kind of like the vertical resolution for these radar profiles. And then at the surface, the footprint of that signal is about 3 to 6 kilometers wide. But we can take advantage of the motion of the spacecraft and Doppler effects to narrow that resolution in the inline direction down to somewhat less than a kilometer. Given the long duration of the mission, we have acquired very dense coverage, especially in the polar regions. This is the spacecraft's in a polar orbit, so it crosses the poles, each pole 12 times a day. We don't necessarily acquire radar data on every polar pass, but on many of them we have. And so the coverage density is almost complete at that sort of 3 kilometer footprint resolution in the polar caps, and even extending out away from the polar caps, it's quite dense in these regions. Down in the mid latitudes, it's a little less dense, but we still have very good coverage in certain areas. We tend to target more the areas where we received subsurface returns in the early part of the mission. And these are kind of denoted with these boxes where they're associated with mid-latitude ices in the white boxes, and then volcanics or sediments in the yellow boxes that are closer to the equator. So again, that dense polar coverage is so good that we're actually able to do fully we're able to do a fully resolved 3D imaging of the polar caps. And so here's a couple of cutaway views into the interior of the polar caps. So we've learned an awful lot about that. But I won't dwell on this, as I think for this purposes of this meeting, we're a little more interested in the mid latitudes where the astronauts are more likely to go. So moving down toward the mid-latitudes, but still fairly high, is the Phoenix landing site. At the Phoenix landing site, this is one of the only places on Mars where a landed spacecraft has actually identified ice. In this case, has been able to dig it around itself and identify ice within the upper 4 to 10 centimeters of the subsurface. Interestingly, Phoenix is the only landing site on Mars that shows clear evidence of subsurface radar returns. Again, remember the coarse, relatively coarse 15-meter resolution. So we don't actually see the top of that ice with the radar. The reflection that we are seeing shown in this red radargram on the right, upper right, at the white arrows is where we see a subsurface return. These are down around 15 to 60 kilometers, or 15 to 60 meters into the subsurface. And we believe this is the base of the ground ice that the Phoenix lander saw the top of. Moving a little closer to the equator, in an area called Arcadia Planitia, the radar detects returns again just below the surface here, shown in the radargram on the right with the right center with the white arrows. These are associated with an area that has some of these terraced impact craters. So you can see from this high-rise stereo image that this crater has sort of these terraced levels within it. And those are pretty good indications of a change in material properties in the subsurface. And we believe that's, again, associated with the base of the ground ices in Arcadia Planitia. Here, the upper, the top of the ice is somewhat deeper than at Phoenix, at least it's thought to be. But it's still not within, it's still not deep enough that SHARAD's able to resolve the top of that ice. Similarly, another area at similar latitudes called Utopia Planitia has subsurface returns. But rather than linking them to these impact craters, we can link them to some mesas around them. Using these sort of topographic constraints, we're able to get at those subsurface material properties and infer that this ice, which extends to depths of 170 meters, covers an area over 1 million square kilometers and contains enough ice that if you melted it all, you could fill up Lake Superior. So those were the kind of the ground ices that are fairly ubiquitous or thought to be across the certainly the high latitudes and extending down into some of the mid latitudes. But there are other ice deposits known as low-bait debris aprons. So these are terrains with surrounding high-standing mesas that have flow-like features. We've known about them since the 1970s from earlier spacecraft, and their morphology has always suggested that ice was involved. But there was a big debate for many years about how much ice was actually in them in the current day. And based on comparisons to terrestrial features that have similar morphologies, essentially the thoughts range anywhere from 10% ice in what's called a lubricated debris flow, or 95% ice in what is essentially just an ice glacier with some debris covering the surface. It wasn't really understood which end member this might be more favorable for these Martian features until the SHARAD radar started getting returns. And as you can see in the radargrams here on the right, the uppermost one is shown in the usual delay time. So it's sort of a cross-sectional view but it's distorted by the fact that the signal travels at different speed through the atmosphere than it does through the subsurface. So if you make a correction to that and assume that the subsurface materials are water ice, then you can correct that distortion and you get the radargram in the middle on the right, where the white arrows are pointing out where we're getting subsurface reflections beneath the ice. And the power of these returns from the base of the ice is so strong that the only reasonable explanation is that these features are comprised mostly of water ice. The debris will be very attenuating to the radar signal. So SHARAD essentially confirms that these are in fact debris-covered glaciers with just a veneer of debris. Again, we're not sure exactly how thick it is, but it's got to be less than about 10 or 20 meters. Otherwise, the radar would be able to resolve it. And it may be substantially thinner than that. So one of the things that we do with the radar instrument is try to assess material properties. And one of the tools for doing that is to take that radar signal that we're getting back from these surface features and kind of break it up into different portions of that bandwidth that I mentioned earlier. And we can use the comparison of how the signal behaves in these different subbands to get an estimate of how much a loss is occurring as the signal passes through these materials. These radar losses are fairly high or relatively high in volcanic terrains, such as the Elysium example shown here in the upper right quadrant of the radargrams. And yet we still do get reflections down into the subsurface there. Here in the Elysium example, we see white arrows pointing at interfaces associated with a couple of overlapping volcanic floats. The strength of those signals is, I'm sorry, the amount of that loss of the signal is somewhat less in sediments. An example of that is shown here in the upper left from Amazonas Planitia, where there's an interface believed to be the boundary between sediments and volcanic layers. And then in the case of ices, such as in the polar caps or even in these debris-covered glaciers that I mentioned previously, the losses are relatively low. And then we get these stronger signals from the subsurface and the base of the ices, as shown at the white arrow here in the Deuteronoilus example. So one thing that's interesting is this analysis, when applied to the examples in Arcadia and Utopia that I mentioned earlier for the ground ices, they actually show greater losses and suggest that the ice fraction might be lower than was originally suggested by the first analysis of the radar data from those areas. Conversely, there are what are thought to be large volcanic ash deposits at the mid-latitudes in an area called Medusa Fossae. And these losses are, for these materials, is lower than would be expected if they were just purely volcanic materials. So there's some thought that these materials may actually contain deeper ice down near the equator, which is fairly exciting. Okay, so earlier I had mentioned that none of these instruments really were designed to look for ice as a resource, but of course they all many of them can contribute to trying to understand ice as a resource. And a number of years ago, when there was a first effort to try to assess human landing sites with a view towards the use of resources in situ, it was realized that a lot of the work that had been done previously either focused on very isolated regions or used a single data set to give an assessment of ice properties. And there really wasn't an integrated study that attempted to bring all these different data sets together to give a more holistic view of where the ice is and what its properties might be. So the examples shown here are some of these single data set examples on the left, where we look at hydrogen content as a proxy for ice from the neutron spectrometer. So the deeper blue regions are at the high latitudes are inferred to be very icy in the near subsurface. They only tell you where that ice is down to about a meter. Similarly, thermal measurements from thermal spectrometers can guide us toward where that ice might be, as shown in the second panel here, where it's the derived depth of the ice table based on these two data sets. And then on a more localized basis, the cameras on MRO, both CTX and the HiRISE camera, have identified fresh impacts in many places around the planet. And some of them expose ice directly at the surface. And so there's an image of an example of that here. So this tells us, it's kind of like a ground truth for where the subsurface ice is, at least to the depth that these impactors will excavate, which usually is only a meter or so. And then on the far right is just a perspective view of one of these high peaks that is surrounded by these debris-covered glaciers. And again, these are kind of a more localized result. So the SWIM project took an effort to integrate all of these different data sets. And it was a bit challenging in that they all have kind of different spatial resolutions, as well as vertical resolutions and depths of penetration. So the graphic on the right gives you, with a like a logarithmic vertical axis here, shows you the depth that these things are sensing. And so for example, the thermal and neutron spectrometer column on the right shows that you get information between the very surface and about a meter depth. And then for the radar, we actually glean some information from the reflection that comes directly off the surface. That actually has a sensing depth of about 5 meters. So we can make some inferences about where ice may be present based just on the SHARAD surface reflection down to about 5 meters. But you can't really tease out any layering within that upper 5 meters. And then on the far left is the SHARAD discrete reflectors, say, from the bases of these ices. And that generally ranges between about 15 and several hundred meters depth. So there's a gap there between, say, 5 meters, and really for fully resolving layers, the gap is between about 1 meter and about 15 meters. Now, using imagery from the cameras and surface topography, we can get at the geomorphic expression of the surface, and particularly by comparing those to terrestrial analogs, we can make some inferences about the presence of ice and perhaps at what depth that ice might be. So the geomorphic data is critical to try to fill this sensing depth gap from the geophysical instruments. It doesn't, again, allow you to make, very precise resolution of depths, but it does help at least qualitatively fill in this gap. Okay, so jumping to results from this effort. It's a large team of folks that looked at all these different data sets, and we came up with a scheme to try to integrate them together that we call ice consistency. And for each of the subsurface properties that the individual methods measures, we assigned values of ice consistency that range anywhere from -1, meaning that that data set is wholly inconsistent with the presence of ice, to +1, where that means the data set is wholly consistent with ice being present in a given mapping pixel. And then we produce a composite of that ice consistency from all the different data sets, since we now have them all on the same scale of consistency. And then we can produce like a map like I'm showing here, where we have the average composite ice consistency from all the different data sets. And here they're sort of averaged across the 3 different depth zones. So this gives you kind of a feel for where one might expect to find buried subsurface ice. And the intensity of the blue here shows a higher level of confidence in the presence of that ice. And we can, having produced this method of analyzing the data, we can separate it into different things. So for instance, this map shows that same ice consistency across the data sets, but only for the 0 to 1 meter depth zone. So you'll notice that a lot of the mid-latitude areas have sort of dropped out of the map here, but there still are, some of the lighter blue areas are extending down towards the mid-latitudes in areas that would be accessible to human landings. And for this map, also showing here these colored dots and red X's that indicate where fresh impacts have been identified using the MRO cameras. Sometimes, as I mentioned, these impacts will expose buried ice. And so the green dots show where we're very confident that there's a definitive detection of ice in one of these craters. The orange dots are craters where we have a somewhat questionable detection of ice. The ice is probably there, but we can't be 100% sure. And then the red X's show impacts that that don't show any evidence of exposing ice. Now, it's important to note that the once that ice is exposed at the surface, after a few months, the exposed ice will sublimate away and potentially also be covered by dust falling out of the atmosphere. So if you don't re-image the site within a few months after the impact occurs, you might miss the ice. So some of the red X's could actually have exposed ice. We just didn't catch it in time with the cameras. But an important correspondence here, though, is if you look, you'll notice that the vast majority of these green and orange dots fall within the areas that from the other data sets, we have inferred the presence of ice through this ice consistency method. So that gives us some confidence that the method is reasonable and doing what we expect it to do. So that in this case, the impacts essentially are serving as ground truth for these geophysical inferences from the remote sensing data sets. And the reason I'm using the 1 meter depth zone for comparison is the vast majority of these impacts only excavate within the upper meter or so of the subsurface. How am I doing for time?
It is 1:32 and our next speaker is scheduled at 1:45 and I believe he is.
Okay, so I'm about to wrap up. I just wanted to mention, so this SWIM project has been feeding directly into plans for next generation orbital radars. One of the proposed missions is a so-called International Mars Ice Mapper, which would be the first mission really that's fully designed to go after ice as a in situ resource to support future human missions. So SWIM is helping define exactly how this new spacecraft would be set up and where it would target in the mid-latitude. So that mapping of where those ices are is feeding directly into plans for this upcoming mission. Of course, it's not been fully approved by all the different partners yet. So we'll see how it plays out in the current environment. This ice, of course, isn't just of interest as a resource. It does inform us about the climate history on Mars, the presence of that ice, where it is, how long it's been there, is important to understanding the past history of Mars. And of course, as a resource, it would be critical for drinking water, doing farming in the habitats, providing fuel by splitting the hydrogen and the oxygen. And then the ice can also be used in construction, as shown in this idea here, this concept for a Mars base, that rounded feature that serves as a habitat is actually protected and shielded from radiation by water, ice on top of the habitat in this scenario. So just to wrap things up, this radar sounder has really shed a lot of new light on our understanding of the polar deposits and their connection to climate, as well as revealing that these mid-latitude glaciers are very ice-rich. And the debris that covers them is fairly thin. It's thinner than we can resolve with the radar. Along with those glaciers, we get important information about ground ices that are more extensive around the northern plains. And both the glaciers and the ground ice are in zones where they're accessible to human missions. The radar sounding's also given us a lot of important insights into non-ice terrains like volcanics and sedimentary terrains that are going to be of scientific interest, both for future robotic missions and human missions. And in general, future radar sounding plans promise new discoveries, importantly about the depths to the top of the ice, but also about new insights into Martian geology and climate history. So I'll stop there, and I'm happy to take any questions.
Thank you very much. Everyone, please remain muted. Students, please mute yourself. I think there's some delay in the muting. Okay, if you have questions, please. I found them. I found the team. If you have questions, please raise your Zoom hand or type in the chat. We have about 9 minutes before our next speaker, is presenting. Karun, you have any questions? You usually have good questions.
No, ma'am, not today.
Okay.
So it's very early here. My head is hurting a bit.
Oh, okay. Well, just rest. Why I would say to Dr. Putzig, why do we care about ice on Mars? How does that affect a human mission? What's the bottom line?
Yeah, absolutely. So one of the reasons why back in 2015, 10 years ago, when they had this human landing site workshop down in Houston, all these scientists and engineers got together and talked about the logistics of sending humans to Mars and the cost of shipping everything that the humans would need from the Earth all the way to Mars and landing it on the surface. And it's exorbitant. One of the really expensive things is sending all the fuel you need to then launch your rocket back off of Mars to come home. And it's really kind of cost prohibitive. And so it was realized that we needed to find resources at the surface to figure out how to bring the cost down to something sensible. And we know that there is this ice there. And we also know how to make rocket fuel by breaking down water and reacting it with carbon dioxide. And conveniently, the Martian atmosphere is all carbon dioxide. So basically, you can make methane from the atmosphere and the water from the ice and generate fuel there on the surface of Mars. In principle, you could even do it robotically and send things in advance to make this happen. So the fuel is ready and waiting for you when you arrive. But in any case, for this reason alone, the ice was really, it was decided that this ice was a precious resource and we needed to understand more about it. And that's what prompted the creation of the SWIM project. Of course, there's all the other side benefits that I mentioned, like the use of that water for drinking and for growing crops, and actually for construction as well. I mentioned the case of using it as a shield for landed habitat, but you would also want to use that for, say, making concrete on the ground so you can build a proper landing pad. So when you land a rocket, it's not throwing debris all over the landing site and maybe impacting existing habitats if you're coming in on a second mission.
Yeah. And what about, drinking water? I think some of the students may find that is important. Can you drink the ice? How do they get the ice to be drinkable?
Right. So another project that I didn't mention that I've worked a little bit on is called Red Water. And basically it's engineering design for how to access this buried water ice. Essentially what you do is you drill down into the subsurface with a thermal instrument at the end of the drill, and then you melt out a cavity of water within the ice. And then you kind of circulate it to help melt more ice and build the size of that reservoir down there. And then you pump it back up the drill stem, and there you have your water ice. And of course, you're going to have to treat it to make sure it's not going to poison you.
Right.
There are like poisonous, we know about poisonous chemicals that exist on the surface of Mars. So we would need means to clean that water up. But we know fairly well from terrestrial experience here how to clean up water sources. So that technology then could be used. And incidentally, this drilling and melting of the ice, we're already doing that here on the Earth. This is how we supply water to people at the South Pole of the Earth who go down onto the ice cap to do scientific work down there. They're using these so-called Rodriguez wells to provide the water supply to the South Pole Station.
Great. And we have some, thank you very much. Mohammed, you have a question? Briefly, we have 4 minutes before the next speaker.
Thanks, Mrs. and Mr. for this interesting points. I'm Mohammed Sheikh from Syria, from Sarai Smart School team. I need a question, please, Mr. And thank you about this important points. About the ice consistency values. Can I get this consistency or this ice consistency from the swim or from the SWIM mapping itself, or from the performance of cameras and SWIM mapping?
I didn't entirely follow your question because there was some cutting out of your voice, but I think you're asking about whether you can get your hands on these mapping results from the swim team. And yes, you can. They're freely available on our website, which is swim.psi.edu. So yeah, feel free to go look for it. If you just do a Google search on Mars swim, you should find them right away.
Thank you.
Thanks.
And if you could drop that after the questions, drop that link in the chat, that would be great, Dr. Putzig. Laksh, what can we do for you?
Yeah, thank you so much. My name's Laksh. I'm from Team Solace. So basically, my question was, what exactly do you think water will have an effect on as a form of energy, like particularly geothermal activity? And second thing, why do you think water, subsurface water, is mainly found in the northern hemisphere and not the southern?
Great questions. So there's not any current direct evidence of geothermal activity that extends to the surface. There are some detections in of certain gases in the atmosphere that suggest that may be a possibility, but we really haven't actually seen it happening. That said, there are terrains that have very fresh-looking volcanic materials. And so it's thought that there could be potentially, modern day volcanism occurring. We just haven't seen it happening yet. And associated with that, they're likely to be geothermal kind of sources as well. So, I think, again, the instruments that we have currently weren't expressly designed for detecting those sort of features. So we do the best we can with the instruments that we have. But one thought is that for designing future instruments, you might want to figure out exactly how you would detect those kind of things. Say with a very high resolution imager, more high resolution than the current high-rise camera. And also other detection methods for gases or other excretions from these features. Could you repeat the second part of your question?
The second part was like, why do you think there is a lot of subsurface ice in the northern hemisphere while not in the southern hemisphere?
So it's not clear that that's actually the case. One difference, though, between the north and the south is the north has these much lower lying, smoother plains that we can better, and they're more amenable to the radar signal passing through and detecting the buried ice. In the southern hemisphere, it's higher standing and it's much rougher, very much a cratered terrain. And there are indications, especially say from that neutron spectrometer, that there is a similar amount of very shallow ice at the highest latitudes. And that is likely to extend down into the mid latitudes as well. But it's much more difficult for us to find it with the radar instrument because of the way it was designed. Another factor that you may have noticed in the map, some of the areas were blacked out. Well, those are at such high elevations that it's unlikely we'll be sending human missions there. So we were guided by NASA in our mapping, and they're like, don't bother looking in these regions because they're not of primary interest for human landing sites. So those blacked out regions likely do have some indications of ice from these various instruments. We just didn't apply our analysis to those areas because we needed to concentrate our efforts as we had limited time and resources to carry out the work.
Thank you so much. And for respect of your time, Dr. Putzig, I appreciate you being here. I've answered some of the questions in the chat. If there are more, if you'd like to stick around, you are very welcome to. And I appreciate so much your time. And students, next we have Ken Brandt speaking. Ken Brandt is the director of the Robeson Planetarium, and his title is Landing Site Selection. So a lot of these water questions may come up in this talk. You have the floor, Ken. Thank you, Than, very much.
Thank you, Nicole.
I'm unmuting. Okay. And I turn my video on here if I can find the button for it.
Okay, and we can see your presentation.
Okay, good. All right. There. Okay. So my video should be starting. This is how you doing,
gotcha.
everybody?
Hi, welcome.
Welcome aboard. Well, thank you. Thank you for having me. So you're going to land on Mars. Apparently, that's the design here, right?
Yep.
So how do you figure out where on this big planet you're going to put your spacecraft down? That's a big question, maybe the biggest of questions, because if you don't land safely on Mars, you can't do anything else involving human exploration on surface. Okay, you might be able to bring a shuttle down there or whatever, and send a shuttle in the first place. Anyway, all right, so I'm going to advance the slide up here. Okay, so let's talk about those that have experience, the robotic missions of NASA and some other countries as well. More recently, China and Russia have gotten into the landing on Mars game, or China has, Russia is going to. So the first parameter, it's got to be reasonably flat. Wherever you're going to put your thing down has to be reasonably flat. Okay? You just got done hearing all about where the water is, so you probably want to follow the water, okay? Because that's going to be a ready source of that in situ resource that is going to be so critical for your success. When you are going, you probably, the rovers, Vikings, Curiosity, and Perseverance were all seeking organic compounds. That was their primary mission. Curiosity certainly not primary mission, and Perseverance definitely, because we're looking for life on Mars. Evaluate for potential past and current life, Vikings and Perseverance. Sample return from Perseverance, of course. The ability to do reconnaissance and scouting ahead of the rover, courtesy of the helicopter Ingenuity. Ingenuity is going to be a big part, or spacecraft like Ingenuity or Mars craft like Ingenuity are going to be a big part of your exploration in all likelihood. The usual mantra is to land on a safe spot and then drive to where the goodies are, whatever the goodies might be, but in your case, you want to land and set up shop. And you hopefully want to land, if you've sent other spacecraft carrying other supplies, you want to land in their neighborhood. So the landing site has to support multiple landings in all likelihood, and it should also support the space for your habitat. So you got to factor that in. Okay. So this is the surface map of Mars that shows where everyone has landed so far, successfully or otherwise. For example, the Beagle 2 landed on Mars, but in lots of little pieces, apparently. But you can see all the green landers. Those are successful missions that are currently up. They had successful missions on Mars. Opportunity, Perseverance, Curiosity. On my screen is behind all the images in the gallery. And Vikings 1 and 2 are also behind the images in the gallery. I want to turn your attention to Phoenix because, as Dr. Lutzig was pointing out a minute ago, some ice is very near the surface. And you might recall when Phoenix blew out the surface dirt, underneath it were pads of water ice, literally plates of ice underneath the lander. So the planetary protection folks didn't get a hold of the Phoenix landing site and study well enough to know that there was ice 6 inches down, right near the surface. Okay, one of the advances that you may want to take use of or make use of as you're landing your spacecraft is terrain relative navigation. That's a special kind of radar or LiDAR that uses the radar to determine safe and not safe landing sites. The areas in red were unsafe for Perseverance to land. And this big red ridge, I don't know if you can see my cursor. Nicole, can you see my cursor? My arrow?
Yes.
Okay,
Yes.
good. That's the edge of the delta in Jezero crater. If you want a landmark reference, this is the bit of the delta called the butte that was sticking out over here on one side. Well, Perseverance landed far away from the delta, roughly half a mile. But look where she landed. She landed in an area about the size of a parking lot, like a standard grocery store parking lot. In America, those things are about an acre, maybe an acre and a half, depending on the store. Okay, so in a square acre, they put this thing down on Mars in that little safe zone in between the two nasty red zones there. So you might say they threaded the needle. But this is one thing that this gives the terrain relative navigation gives Perseverance the ability to navigate and to actually figure out where exactly it wants to land, similar to what you will likely be doing if you're the pilot of this thing. Okay, and how about us? What constraints should you consider when you're deciding on a landing site? How readily available are resources at that site? In situ resource utilization, or ISRU, is you'll see that acronym a lot over the next few weeks. Again, subsurface and surface water ice might be a handy thing to have. Building materials might be a handy thing to have. You want friendly geology for landing, so you don't want to land in a boulder field. You want to land cobble size or smaller on the surface there. Radiation risk mitigation and availability of marketable minerals, perhaps. Perhaps you may want to factor a little cash raising into your exploration of Mars. Okay, so this is another map showing potential for glacier regions in the survey down to the mid-latitudes in the northern and southern hemisphere. As you can see, to get to one of your questions last time, the distribution of potential glaciers looks about equal over the hemispheres. If anything, it might be more dense in the southern hemisphere. Certainly in parts of the northern hemisphere, they're very dense. So these are all potential places where you could land and tap a well, or dig down and literally dig the ice out of the ground and bring it back to your habitat, purify it and drink it, or whatever else you're going to do with the water. So water is the most important of these resources for all the reasons Dr. Lutzig just got done laying out for you, and probably more. I would be a fan of fuel cell utilization for the generation of power on Mars. Since you need a lot of solar panels, you're going to try and generate solar because you only get 0.43 of the insolation that you have on Earth. So you definitely want supplemental power for when it's dusty. For example, if you get an opportunity killing class dust storm, then you want an alternative to solar power ready at hand. Now, geothermal is a possibility depending on where you go on Mars, but there hasn't been very much survey to talk about the temperature at depth and where you'd have to sink your pipe to with the liquid ammonia, excuse me, or whatever it is you would use as the fluid that's passing heat or cooling along to your habitat. Okay, why should you be concerned about radiation? Well, it's pretty easy. Radiation will kill you. The graph on the right, if you minimize the gallery, you'll be able to see the graphic on the right. 1 sievert is equal to 1,000 millisieverts, as you might guess. If you look at these bar graph indicators here, you get reminder, of course, this is a logarithmic on the y-axis and not a linear scale. Okay, so we have logarithmic going up the y-axis here. What they don't show you is that you have to come back from Mars, hopefully, unless this is a Mars 1 style mission, you're going to stay. You're planning on coming back at some point, rotating crews, which is probably a sane idea anyway, for lots of good reasons that have nothing to do with equipment, have everything to do with what's going on in our brains and all the ways that our brains malfunction when in isolation for a long period of time on a foreign planet. Now, what's not considered in this graphic here on the right is the return mission, the 108 return transit from Mars. So that's another third of a sievert. And the incidence of cancers, according to the UN's Office of Radiation, the acronyms up there, UNSCEIR, is that the influence of the ionizing radiation increases the risk of cancer linearly at a percent of 5.5% per sievert. Now, I contrast that with the evidence from the astronauts who have actually been exposed to fairly high doses of radiation due to prolonged exposure on the space station, for example. Thinking of people like Shannon Lucid, for example, who spent more than a year up there, or Sonny Williams, who was also another long duration flyer. So far, none of those astronauts have succumbed to any cancers that we know about. Okay, I'm going to stop here and ask if there are any questions about anything so far, because I saw the activity is pretty active in the chat.
Let's see. I was answering some questions in the chat. Jad has a question. Go ahead, Jad.
Hello, ma'am. I'm Professor Brandt.
Hello.
Firstly, thanks for the most awesome and professional presentation that you have just show us. But I want to ask about your opinion of something about
Okay.
the dust storms. What about
Yes.
the percent of dust storms? It's more likely in the northern hemisphere or in the southern hemisphere, and what should we consider about the speed of wind, the wind speed when we land on the
Okay,
pilot
first thing you should
location?
know, but all right. First off, I'm going to defer immediately to another expert you have talking to you at some point in the next couple of days. He's a fellow solar system ambassador, as I am, Tony Rice. He's the meteorological expert, and he is the man to answer your question. I can't, because I have no idea. Okay, and I'm not going to try. I will say, though, that the wind pressure is negligible because the atmosphere is so thin that even it blowing at a good clip, it's not a lot. It can't do some of the things you saw in, for example, The Martian. Like it can't drive a metal pole through somebody. The wind just is not that powerful. So that, the powerfulness of the wind and what it might do to your habitat is not that big of a consideration. What is the clarity of the sky and your ability to operate outside during a heavy dust storm, your own visibility being a limitation as well. Okay, so these are regions on the globe of Mars that have a significant magnetic field. Okay, and a light magnetic field might be enough to help you deflect some of the surface radiation. But the most simplest way to avoid surface radiation is to bury yourself somehow. You put your habitat into a cliff, like the cliff dwelling Native Indigenous Americans in the Colorado area and Arizona, in the southwestern United States, like the Pueblos, not the Pueblos, excuse me. Anyway, or you might want to literally bury your habitat, or surround it with some kind of substance that will block the radiation. Now, Dr. Lisa mentioned water, ice, of course, but water would also function very well if you just had your water tanks external to your habitat. You get some radiation protection from the water itself. Problem is, water is heavy, so you have to incorporate that in your design. Okay, so let's talk about lava tubes for a minute. This is the Tharsis region on Mars, the volcanic region in the northern hemisphere of Mars. And you can see all these volcanoes littering the surface here. Kind of reminds you of an archipelago over a hot spot, like Hawaii, for example, in the United States. This is one example of volcanoes that form over a hot spot as the crust moves. So I don't think we have the plate tectonics going on Mars that we did on Earth. Again, I'm not sure, but I don't think we have that going on. But what we do have going on, all those little red squares are places where lava tubes exist. And a lava tube might be the simplest and most practical habitat of all, because all you have to do is seal both ends of the thing and pressurize it. Now you've got air and you've got a habitat. You've already got walls and ceiling. You don't have to bring them or build them. So, lava tubes might be the way to go in terms of landing sites. You obviously want to get outside often enough where you're not succumbing to submariner syndrome, the being shielded away from the sun too much. So obviously there are ways on the surface to put yourself in a place where there's not very much radiation, if you are exposed to any from the surface. Okay. And another constraint you might want to consider is this bit. And I hope this video plays. All right.
Yeah, I
Are you
don't.
seeing a blank screen essentially?
I don't. It's
Okay,
just
good.
staying.
That's good. It's just loading still. There it
Okay.
is. Okay. So we're going to bring him up to full screen rather. Turn on our closed captioning. Full screen. My computer is acting very slow today. I apologize for that.
It's okay.
We might have to do it full screen. It's coming. Taking its time loading. Okay, little background. This is the decision room for where they're going to decide to land the Apollo 15 spacecraft.
You may have to reshare the screen with the YouTube video because I still see your slide.
Okay. Hold on, Dave. Okay. All right, so I'm stopping the share for a minute.
Mm-hmm.
Okay, and then I will reshare my screens. Zoom. No, wrong one. This Zoom. Okay, sorry. I'm having a little bit of technical difficulty getting to the screen that would show sharing.
It's okay. Do you have the green square with the arrow at the bottom?
Yeah, I see. Now I see it. Okay, it just came up.
Yeah,
All
it disappears sometimes.
Okay, so I don't want the Zoom meeting. I want this one. No, I don't want that one. Oh, all right. Okay. I'm gonna try sharing my screen one more time.
Okay.
There we go. There she blows. Now, let's try this again. Nope. Wrong video. Um, okay. In the name of expediency, try this again. Can you see a video screen up here?
I just say, it says you are sharing your, oh, here it comes. Here it comes. Apollo program.
That's it.
Yep. There it is.
Okay.
I don't hear anything though.
No offense,
There it is. It's just slow.
that. Okay. Oh dear. Okay. Sorry about that.
We have about 5 minutes before our next speaker.
Okay. Okay, so grandeur is something you may want to consider in amongst all your planning. So at this point, I'm going to stop and turn this over for questions. And so the next speaker has time to check their text and all that stuff.
If you send me the link or just put it in the chat, I can do that. Karun, please ask your question.
Yes. My question was that you mentioned the caves of Mars as possible protection from cosmic rays and solar flares, radiation protection. Do
Right.
you think these caves could also be used as possible greenhouses for agriculture, if possible, on Mars?
Oh, again, you're a little bit outside my comfort zone of knowledge, but I would assume so, with the proper, growing equipment and the lights and everything you would need, since we would have no sunlight, unless you were using mirrors or something to bring it in there. Anyway, okay, I'm going to try and put the link to this video in the chat.
Okay, Johan has a question.
Go ahead, Johan.
Yeah, hi there. So sorry, this question is slightly, well, huge, but yeah, I'll go ahead. Given that Mars is a very thin atmosphere, about 0.6% of Earth's, and a reduced gravity, how do these conditions for landing from a geological perspective, especially when targeting geologically rich but risky terrains like crater rims, dry river deltas, or volcanic regions?
That's a good point. The atmosphere makes landing more difficult because you can't you can use a parachute to slow things down, but you're not going to be able to parachute and land. Something very instructive might be to just watch JPL's recording of the landing of Perseverance on Mars. Because when they landed Perseverance, they showed you a pretty good look at what it would look like to actually land on Mars, because they had cameras everywhere in this thing. They wasted no time. They put cameras on the sky crane, camera on the top of the rover looking up at the sky crane. so the engineers could figure out what was happening with the parachute when it unfurled, for example, um, and a camera looking down. So you also had the astronaut's eye view. If you were trying to land Perseverance on Mars, you have the view from the pilot's seat. So, okay, so I shared the video link, yes?
Yes, I have it. And Amir said, you mentioned radiation mitigation. Is the radiation powerful enough to hurt the astronauts when going out for short periods of time, or can we just neglect it?
Well, I would say you will probably be doing the same thing X-ray technicians do, and that is you'll be wearing a badge that is sensitive to any kind of radiation that would make it through your suit. Because remember, things like beta particles aren't going to get through your spacesuit, much less to you. So you don't have to worry about those too much. But alpha particles and the more complex, larger cosmic ray particles, they'll do you. And you don't know it's just like going out in the sun right now. You don't know if that particular instance of going in the sun for half an hour is going to give you melanoma.
Right. And then there's some questions about volcanoes.
Okay.
One of them is about a lack of information about volcanoes, and the other is I think if we want to land on these volcanoes, we will have a problem, which is the area I think is really risky and not flat enough. Is that right?
Well, the slopes of I haven't looked at like the cone of Mount Olympus, for example. So I can't really answer that question intelligently, except to say there are bad reasons. There are reasons not to land on top of a volcano for all kinds of good reasons. Number one, remember that whole getting near in situ resource? If you're a couple of thousand meters up and the nearest water to you is a couple of thousand meters down, that's a bad place to land, I would think, unless you
Yes.
got a lot of pipes, you
Right.
know.
And I would add to that, there is a lack of information about a lot of stuff on Mars because there are no people there. We only have a few robots and a few orbiters. So yeah, we need lots of research. That is why the Mars Society hosts this program, so we can inspire young minds to do that research in the future. I don't think the next speaker has arrived.
Okay.
Dr. Kuznets, if you're here, let me know. If not, we'll just do you have a couple more minutes for Q&A,
Of
Ken?
course. Yeah, go ahead.
Um, Someone said, I thought that alpha particles are unable to even penetrate human skin. Wouldn't that make gamma particles the only main concern?
I'm not sure. I'm not going
Okay.
to answer that one definitively because I don't know enough about radiation, which rays penetrate and which don't. I know about beta rays,
I
which are
want to
basically
answer.
electrons.
I
Go
want to
ahead.
clarify something for the students. Each professional expert we have speaking has a specific area of research. So a volcanologist is not going to know much about astrobiology. So you have to keep your questions in the right area of expertise, just so you know. These scientists spend their entire lives studying and researching a specific niche for planetary science. Jeremy, can you ask your question, please?
Um, Hello. I wanted to ask if prolonged exposure to radiation could cause astronauts to have radiation sickness.
Absolutely. Given a high enough dose, like say if there's a CME event from the sun, the sun puts out a whole bunch of radiation at one time. It's possible. As a matter of fact, we now know that the Apollo 17 mission missed uh, a game over nuclear outburst from the sun that had they been exposed to it, they would have indeed died of radiation poisoning because the command module and the return module for the Apollo ship had no radiation shield, essentially, other than the hull itself, whatever the hull was made out of. But it was thin, you recall, because they wanted to save mass wherever they could, because they were trying to get all the way out to the moon.
And Ken, I'd like to reiterate something I've heard Dr. Robert Zubrin say many times. Space travel is dangerous, but we have to take the dragons off the map. People will die on these expeditions. There's just no doubt about it. But if we didn't take that risk, we wouldn't have explored the entire planet back, a few hundred years ago. So it's a risk reward ratio decision. Johan from Team Genesis.
Hi, sorry again, but this is actually an extension to my question that I wanted to clarify. I'm so sorry if I'm bothering you with this, but
Yeah, go ahead.
in what ways do factors like terrain slope, surface dust thickness, rock distribution, and altitude above mean Mars level, aeroid constrain landing systems design and site selection?
All right, you're gonna have to give me the second half of that one again. I'm sorry.
Yeah, slow down and make it a little more clear. You're talking very fast.
Okay, yeah, sorry about that. In what ways do factors like terrain slope, dust thickness, rock distribution, and altitude above mean Mars level, aeroid constrain landing systems, design, and site selection?
Greatly. In general, if you have a map lander you're trying to put down on Mars, the more help you can get from the atmosphere to slow you down, the better. So you want to be below mean altitude if you wish. From what I'm seeing when you look at a global map of Mars, it seems like the more of the interesting places are down there anyway. Slope affects your landing because you can only tolerate like up to, I think it depends on the spacecraft that's doing the landing. Okay, I know for Perseverance, it could not tolerate more than a 15-degree slope. Okay, so the slope on the landing site itself could not be higher than 15 degrees. And of course, particle distribution and size is definitely going to matter. If you have cobbles or small boulders, it's going to be a lot harder to land on than if you have gravel, like Opportunity landed on.
I'm trying to mute that person. Sorry about that. Somebody is unmute. Okay. Mohammed, please ask your question. Can't hear you at all. Mohammed, there's a lot of interference. That it was very staticky. Please type your question in the chat. We couldn't hear you at all. Karun?
Ma'am, I actually had a question for you about something you mentioned earlier. My question was, you mentioned earlier, quoting Dr. Robert Zubrin, that people will die. There is no doubt about it. Ma'am, do you mean to imply that at least one of these missions will be a suicide mission? And if so, what should we tell the astronauts who know, or do they not know, that they're going on a suicide mission?
Well, I wouldn't call it a suicide mission. I would say that every single astronaut or pilot or ship captain or human that crosses a street at any time knows there is a risk of death. I could get hit by a meteorite in my office right now and die. So we know we are under constant threat of death. So every single astronaut now, Ken, I don't know if this is true or not. Did the lunar astronauts have suicide pills? Is that true?
I don't know the right answer to that question.
Okay, I've heard rumors and I've seen things, but I'm not 100% sure. But I would imagine I would want that if I was stuck out floating in space. I wouldn't want to starve to death in space, or I just take my helmet off. But yes, every person knows there's always a risk of death. The lunar astronauts know, the ISS astronauts know, the space shuttle, the Dragon capsule, the Russian astronauts, they all know. Yes. And it doesn't stop them from exploring.
Right.
Yes,
Okay,
ma'am.
our
So
next.
line up on the block. Sorry, go ahead.
Go ahead, Ken.
No, that was it. I was just going to say they're still going to line up around the block to apply to go.
That's right. Just
Until
like a
time
few
comes.
years ago, probably before Karun was born, there was a company who put out a call for astronauts to go to Mars, and everybody had to pay like $75 to sign up. And in a week, they had 250,000 people signed up to go to Mars, just like that. Now, that company collapsed and folded. But the fact that 250,000 people signed up in a couple weeks is pretty amazing, all knowing the risk.
Right. They
Okay,
knew it
and-
was a one-way mission.
right. And it was a one-way mission. They had no plan to come home. Yes. Mohammed's question is, can TRN, I don't know what that is offhand.
Terrain relative navigation.
Oh, sorry.
Okay.
Been a long week.
No, it's okay.
Terrain relative navigation, only enough in the map that have a lot of smaller obstacles. And are there any other navigations that I can use to support with TRN?
Well, you're going to want to have a good pilot behind the controls of your lander. You definitely want to give them the authority to take over manual control, no matter how good the AI and the machines get. Okay. These craft are designed for people to fly them, which means people know how to fly them better than the machine does in general. That is, if you're going to put a pilot, an astronaut pilot behind the wheel of a starship or something that's going to the moon, they're going to know how to land that thing, okay, better than the machine can, given uncertainties like what you were saying about the size of the particles. I'm pretty sure the size of the particles that were deemed the red zone, if you will, were anything larger than 6 inches across. Pretty sure. I could be wrong, but that's a guesstimate. Okay. So anything bigger than 6 inches across, no good to land on if you can avoid it.
Okay, let's take one more question from Rosgar.
I was gonna ask, what if about the suicide mission, you know that there's a risk of death, but what if the mission is guaranteed for death? Like, you know that they are gonna die in a while, like it is guaranteed, they already know that, but they can still sign up for the mission. Is that ethical?
That's a question that
That's
has
a
been
really good
pondered.
question.
Yeah, that's been talked about and discussed. Yes, yes, yes. Agree, Ken?
Oh yeah, definitely. That's a factor. And knowing you're not coming back, do you sign up anyway? And Riskar's question, which is way more for the legal scholars than for me, should we?
Right.
I mean, should we in the first place offer that opportunity to people? Or should we not attempt a suicide mission like that? And again, I hesitate to use the phrase suicide mission. A one-way mission. How's that? Where you're going to run out of resources at some point.
Yeah.
Right. And I suggest everyone watch the movie The Martian if your parents will allow you, depending on your age. The Martian movie was written by Andy Weir and was based about 85% on Dr. Robert Zubrin's Mars mission. So it's very much based on what we're planning to do here. So watch the movie The Martian with what's his name? Who knows his name? The famous actor.
Oh, it's not Brad Pitt.
No.
No. Oh,
you guys
God.
know. The Martian. You guys know The Martian.
Okay.
Watch that book. I mean, watch.
And besides, you might get some decent ideas for your habitat.
Exactly. Exactly. He got stuck on Mars alone. I'll just tell you that. And so, Matt Damon, thank you. Thank you. Thank you. Yes, watch it if your parents will allow you to, if you're old enough. Well, our next speaker must have had an emergency because they have not shown up unless you're here and I didn't see you come in. Ken, thank you so very much for taking extra time to talk to the students today. Students, we will meet again tomorrow at the same time we met today. We have 2 speakers tomorrow. Please email me any questions. Please go to the team name spreadsheet I just shared. I sent it via email to every student and I put it in the chat here. Put your team name in the spreadsheet. Make sure it's simple and easy to spell and easy to pronounce for everyone. All right. Thank you guys. I'll see you tomorrow. Bye.
Thank you.
Bye.
Bye.
Thank you.
Bye,
Bye.
ma'am. Bye.
Bye, everybody.